Ladies and gentlemen, thank you for joining us today. We are waiting for the last few attendees to log in, and we will be getting started shortly. Again, thank you for joining us, and we will be getting started shortly. Ladies and gentlemen, thank you for joining us. We are waiting for the last few attendees to log in, and we will be getting started shortly. Hello, and welcome to Impacts from Firefighting Foams, Policy, Regulations, Characterization, and Treatment for PFCs. My name is Suzanne, and I will be in the background answering any WebEx technical questions. If you experience technical difficulties during the WebEx session, please dial 1-866-779-3239. Please note that as an attendee, you are part of a larger audience. However, due to privacy rights, we have chosen not to display the number or list of attendees to everyone on the call today. As a reminder, today's call is being recorded. We will be holding a Q&A session at the conclusion of today's presentation. You may ask an online question anytime throughout the presentation today by simply typing your question into the Q&A panel located on the right-hand side of your screen. Just type your question into the text field and click Send. Please keep the Send to defaulted to all panelists. With that, we invite you to sit back, relax, and enjoy today's presentation. I would now like to introduce your moderator for today, Rick Cox, Vice President at BMT Designers and Planners. Rick, you now have the floor.
Okay, thank you. Hello, everyone. On behalf of the Society of American Military Engineers, I would like to welcome you to today's webinar. I'm Rick Cox, and I serve as Chair of the SAME Environmental Committee, who is hosting this webinar. The mission of the Environmental Committee is to create value for our membership through educational opportunities, professional forums, outreach, and business programs. The Environmental Committee is focused on the collaboration of SAME members and government staff working on environmental issues. If you're a member of SAME and interested in participating in the committee, you may join by following the instructions on our webpage, same.org/environmental. Additionally, you're welcome to follow us on LinkedIn. This webinar would not be possible without the tremendous efforts of Tim Fitzpatrick from SGS Access Laboratories, who leads the Environmental Committee's webinar and education programs. Additionally, I would like to thank Bill DiGiuseppe and his colleagues from CHM Hill for their efforts in organizing this webinar. We have 100 people registered for this event. Feel free to type questions in the WebEx Q&A box. We will answer as many questions as time allows during the webinar. Afterwards, you will be routed to a survey page. Please participate in this short poll so that we may improve future webinars. We're honored to have our first speaker who will discuss DoD perspective on perfluorinated compounds and polyfluoroalkyl substances. Maureen Sullivan is the Deputy Assistant Secretary of Defense, Environmental Safety and Occupational Health. Ms. Sullivan is responsible for DoD policies and programs related to compliance with environmental laws, management of natural and cultural resources, cleanup of contaminated sites, safety and occupational health, fire and emergency services, international environmental compliance and cleanup efforts, climate change adaptation planning, strategic sustainability planning, planning to address emerging contaminants, and many more. Additionally, Ms. Sullivan is responsible for the DoD Native American Program. She oversees the Armed Forces Pest Management Board, the DoD Explosive Safety Board, and the Strategic Environmental Research and Development Program, Environmental Security Technology Certification Program. At this point, I'd like to turn this over to Ms. Sullivan.
Thank you, Rick. Can you hear me?
Yes, we can.
Okay, great. Well, good afternoon, everybody. Thank you for this opportunity. I want to, first of all, I appreciate that the title is The Impact from Firefighting Foam. I'm going to focus on specifically PFAS and PFOA in my remarks today. So let's step back and do a little history first of all. Rick mentioned that I have the Emerging Contaminants Program, and this is a program that kind of does some looking out to the future of where there are issues that may in fact be of interest or impact or create risk for the Department of Defense. And back in the 2000s, our Emerging Contaminants Program, our EC programs, had looked at PFOA, PFAS, and said, there is an emerging risk here. It looks like there's toxicological information that's being collected, that there's interest on parts of various organizations. So they were monitoring this. And then lo and behold, sure enough, in 2009, EPA issued the Provisional Health Advisory, which many of you may be familiar with. So there I want to highlight what I call our first missed signal for the Department of Defense. We have a DoD policy on emerging contaminants, and it has in it a whole tiered process for chemicals. And when there's a public health advisory published by EPA, that is considered a Tier 3 number. And if you read our DoD instruction issuance, it says, oh, that number is of sufficient quality that it does, in fact, trigger a requirement in the cleanup program. So we should have, back in 2009, started to go through the cleanup process, the CERCLA process, to identify where we may, in fact, have had stored or used or possibly released something that contained either PFOA or PFAS. Also in 2009, the EPA's Superfund Office issued a memo that talked about how to use the PHA number in the cleanup process. Well, again, DoD missed this signal, so we kind of missed a window of opportunity there. But what's done and done. Now, I will give credit to our EC program because in 2015 they said, okay, signals are getting stronger again, and we made a decision in December of 2015 to start looking at the supply system. So to look at AFFF to say, where is it in the supply system? Should we start taking action, and in fact directed that we start taking action to control the land releases, so in other words, to stop the releases of AFFF that contain the PFOA or PFAS, as it may be, during maintenance, testing, training activities, and to start removing the PFAS-based AFFF from our local supply stores. So December 2015. A little bit ahead of the EPA action. So then come 2016, as you probably most of you already know, EPA issued the Lifetime Health Advisory in May. But we need to put that in context of what was going on with drinking water at that time and the entire issue about Flint. And so people's perception of we have to ask ourselves, where is the public's perception about the safety of drinking water at large, and what information is coming out from regulators about exposures and risks to people associated with drinking water? So, but what is a Lifetime Health Advisory? Well, one thing, it is in fact advisory. There are no enforcement provisions for people that are purveyors of drinking water. It is advisory in nature. They can choose to follow it or not, but it says, provides context, is that information. But the second thing to understand is the Safe Drinking Water has very broad enforcement authorities on what is a substantial endangerment. So if a regulator feels that there is substantial endangerment, the Safe Drinking Water Act gives them broad authorities. And EPA chooses to exercise those authorities and has chosen to exercise those authorities when it comes to a Lifetime Health Advisory to address a exposure under drinking water. But three, the thing to remember is a Lifetime Health Advisor in LHA does in fact drive a cleanup requirement. So it says, okay, you've got a number sufficient quality now, you have to roll this into your CERCLA process. And that is consistent with DoD policy. And that is laid out in our emerging contaminants policy and in our Defense Environmental Restoration Program. So it's an affirmative signal that we must now start identifying where we have used, stored, potentially released this chemical and determine if there is a risk, if there is a source, a pathway, and a receptor, typical cleanup. So what is DoD doing, which is, I'm sure, what all of you are interested in. So number one, let's start with drinking water. So again, LHA is advisory. However, we, the department, made the choice that where we are, in fact, a purveyor, we are, in fact, going to test. We are going to test and follow EPA's advisory language. As of the end of September, we had tested about 36% of the 480 systems that we operate. So far, only 7 have tested above, and we've taken the appropriate action. Where we buy water, because as many of you may have dealt with our military installations, we have some installations that are actually the purveyors. We have our own wells, we have our own distribution systems. Other installations, we simply buy from the local utility. We hook up to the local utility. Where we hook up to the local utility, say at someplace like Fort Belvoir or Andrews Air Force Base, or they hook up to the local utilities. We're just simply asking them to contact their purveyor and
Okay, it looks like we may have lost Maureen Sullivan. We're having some technical issues. If everyone could just hold tight for a minute, we're going to try to work it out on the back end. Thank you.
Hello? Hello?
Yes, we can hear you.
Oh, okay. So when did you lose me?
The drinking water purveyor.
Oh, okay. Thank you. Sorry about that. Okay, so so bases in the United States, we're asking where they buy from the local utility to go ahead and contact them to see if they are in fact testing. So let me move quickly into the cleanup program. So cleanup. So under our Defense Environmental Restoration Program, DoD instruction, and the Emerging Contaminants program, lifetime health advisory is a good number. It is a number. We should be starting to follow the cleanup process. So using the Defense Environmental Restoration account funds, normal process. Source, pathway, receptor. The priority in the cleanup program is to cut off exposure. So if there is a path to drinking water, then the priority is to cut that off. Now, I can tell you right now, I don't have an inventory of the sites. We're working on that right now. All 3 military departments are moving out aggressively to do the inventory of sites. I can tell you, doing a rough ballpark of having done this for a long time, I'm going to estimate that it's going to add somewhere around $2 billion to our cost to complete in the department all told. Now, I'm not going to get any more Defense Environmental Restoration funds. I'm just going to extend the program out is what it's going to be. It's like any other contaminant that's added. You know, we have sites. We may have a lot of sites where they're already doing cleanup. This would go into the 5-year review process to say, okay, we have a new contaminant at an existing site. We need to add it in to figure out what is the remedy and how do we amend the current cleanup process to add this contaminant at that location. So there are lots of challenges here that have emerged associated with this program that we all have to deal with. Some of them include risk communication. So a lot of the issues that have come out have created problems or created concerns are people not understanding what is the risk if I drink this water and what are the problems associated. We get lots of questions about any presence of PFOA with PFAS versus the lifetime health advisory. We need to do a better job on that. We're also getting a lot of questions on health studies. Are we going to do health studies? Are we going to do biomonitoring? And we were ill prepared to be able to respond to those types of things. As I mentioned, we're getting requests to treat water that has tested below the lifetime health advisory. We were ill prepared to respond to that and to be able to explain what the lifetime health advisory number actually is and how to do that. And another challenge that we've run into is lab capacity. This created a whole inundation into the lab community. It's very important to make sure that there isn't cross-contamination in this process. There are limited numbers of labs. The labs are getting backed up. It's creating a problem. We were ill prepared for this. Now, recently, EPA actually had to update the sampling method and the test method because they were running into a problem. I am not an expert in this field. It was something about linear versus matrix. So for anybody that's involved in testing, you really need to make sure you're looking at the current methodology that EPA published approximately 2 weeks ago, or it could be 3 now. So what is the priority within the cleanup program? Within the Department of Defense, remember, we're on a nationwide risk-based prioritization program. So our first priority must be cutting off the drinking water path. Yes, it would require us delaying lower risk sites, but it must be our priority. But once we cut off the exposure, if we cut off that drinking water, it doesn't matter, there are multiple ways that could help in taking the well offline, putting in a treatment system, providing bottled water. There are various options here. Then we step back and say, okay, you follow the normal cleanup process. So when you think about my opening on the history and context here, if we had followed our actual emerging contaminants policy way back in 2009, we probably would have been well on our way here to have identified and inventorying the sites and figuring out what our cleanup requirement is. And then we would have only been dealing with the delta between the 200, 400 numbers and the new 70 numbers. It would have helped us. So it's a lesson learned to us to be more specific in terms of when we have these numbers and making sure that we're communicating that information and doing what we need to do. So the third thing I want to touch on is the supply system here. So in the supply system, PFAS is no longer manufactured. The new AFFF that we're buying does not have PFAS, but it may have small amounts of PFOA as part of the manufacturing process. So we have a couple of problems here. So we have some of the old AFFF in the supply system. We're working with DLA to get it out of the supply system and make sure that what is being issued out is the new version, the PFAS, without the PFAS. But we have existing fire systems that have the old version in it. And so a lot of discussion about that. And as I mentioned, we've already issued policy saying, you know, don't do uncontrolled releases in land-based applications. We are working on, the Air Force only has made a choice to affirmatively replace it in fire trucks, the existing inventory. We are investing in the CERTA program on a fluorine-free, researching a fluorine-free AFFF, you know, but it's basic research, so it's going to take several years. So in conclusion, lots going on in this area. It's a huge challenge. We have a huge challenge with risk communication. I have to applaud the military departments. They're stepping up. They're doing a great job. I think the lesson learned that we all have is we need to have a clearer understanding when we have a good number and when we need to start the cleanup process. But there are many other PHAs out there, not just PFOA or PFAS, and we haven't rolled them into our cleanup program. There are other chemicals that have preliminary health advisories out there that we haven't rolled into the cleanup program. 1,4-dioxane would be an example. I have questions, and I'm going to be asking my folks about, okay, if we have a PHA, what are we doing in our cleanup program? Have we, in fact, affirmatively addressed it? But the other question I think we all need to grapple with, and my question regularly to EPA is, okay, what's next? I don't like being caught short on this. I want to make sure the department is well prepared and able to respond. I suspect, talking to them, that the next new thing in the water world is going to be the lead and copper rule, but I don't like how ill-prepared we're for this. I'm also cautioning everybody to watch EPA's effort to establish an MCL for perchlorate. Yes, perchlorate is back. EPA's on a pretty tight schedule to issue an MCL. You know, we don't know what it's going to be, not going to say. There are three options here. It could stay exactly where the current advisory is. It could go above it. It could go below it. I contend that the most difficult challenge for the department is if they raise the number, if they may say the current number is too low, that the risks are not there. It'll be hard to back away from that. I don't think they're going to do that. I think it's either going to stay the same or go down, but we have to watch it. So lots going on, a lot of moving parts, but I do want to applaud the military departments for their efforts to step up on this, and for all the contractors that they're using for the support they're providing. It's really been a tremendous challenge, and I think we're doing a great job. So, Rick, I'm going to go back to you. Hopefully you can still hear me.
Yes, thank you very much. It was great, insightful, and I really appreciate your honesty here. The first question that I have is that you've seen an increase and an uptick in emerging contaminants, and as you talk about, use the word ill-prepared, challenging, and such. And so how are you changing your department to be able to respond to this and future contaminants?
That's a good question. Well, one of the things is we sat down and really scrubbed both the policy statements to say where were they weak that we didn't understand exactly what we were committed. So we have, in fact, I should say, we are in the process of revising those policy statements so that we are clearer of when we send that signal that there is a change, therefore you must do something. So both the emerging contaminants policy and the Defense Environmental Restoration Program policy, those instructions are in the process of being revised to make that more, to make it clearer. And then to get more visibility from that Scan Watch Act process that we have under the EC to get that communication out.
Very good. Ms. Sullivan, we have a lot of people on the line who represent laboratories, and how is the department reaching out to them to make sure that, test methods are meeting these new challenges? And are you looking for an increased dialogue with some of these labs?
I defer to Jordan Adelson, our laboratory expert on that, so I'm not an expert in this field, to be honest with you, so I would really recommend that they talk to Jordan in the Navy. He is our lab expert in this area.
Okay. Well, just FYI for yourself, ma'am, we're going to have a panel on PFCs at the Joint Engineer Training Conference in May of next year in Columbus, Ohio. So SAME and the Environmental Committee is very interested in helping the department address this issue.
Okay, thank you.
So thank you for your time. We did not get any other questions. There's still time. If anybody wants to send a question real quickly, we'll ask it. Okay, I think it's time to move on to our next speaker. We have Dr. Christopher Lau, who is the Chief of Developmental Toxicology Branch of the Toxicity Assessment Division in the National Health and Environmental Effects Research Laboratory under the Office of Research and Development of the U.S. Environmental Protection Agency. Dr. Lau received his PhD in pharmacology from Duke University and postdoctoral training in neuroanatomy from the Medical College of Pennsylvania. He is an active member of the Society for Neuroscience, Society of Toxicology, Characterization Society, and the International Society for Developmental Origins of Health and Diseases. He serves on the editorial board for numerous publications. His research interests include developmental toxicology, teratology, neurotoxicology, and health risk assessment of chemicals in the environment. At this time, Dr. Lau.
Thank you, Rick. And I want to thank the organizers of this workshop for inviting me to talk today. So in the past decade or so, there are really hundreds of papers, studies describing the topic that I'm going to talk about, the toxicological effects of the PFAS, perfluoroalkyl substances. So I actually have a pretty tall order when they were asked me to talk. I had to summarize everything in about 20 minutes. So I want to emphasize that what I'm going to tell you, it's going to be a very, very high level. There are plenty of reviews written on this topic, and I would encourage folks to take a look at them. So the chemical of today actually, well, first of all, let me back up a little bit. There are really thousands of these PFAS, perfluoroalkyl substances. And today what I want to focus on is only a subset of this chemical, the perfluoroalkyl acids, PFAS. So there are only 3 groups of these chemicals under PFAS that I know of: the sulfonates, perfluoroalkyl sulfonates, the carboxylates, and the phosphonates. Now, the phosphonate may be somewhat unknown to most of you. It is a pretty recent comer to the field. And I will just say a couple of words on it because we know very little about this chemical. They are manufactured and used as a wetting agent for waxing and coating, and as a defoaming agent in production of pesticides. Only the last few years that's been detected in surface water and effluents from the wastewater treatment plants. And that's about all the information we have. There's very little toxicological results being published. So either people haven't paid attention to this chemical, or maybe they are just not a lot. So I think a lot of work needs to be done on this chemical. So for the rest of the talk, I'm going to focus on the sulfonates and the carboxylates. So the sulfonates, there are in the environment, well, first of all, this chemical is not just one chemical per se, so there are a whole bunch of chemicals within each group. The sulfonate, for instance, there are 3 that are commonly found in the environment. There's C4 sulfonate, the C6 sulfonate, and the C8 sulfonate. And there are more carboxylates found in the environment, so they can range from 4 carbon, the C2, PFBA, the 4 carbon, so the N will be 2. So they range up all to 12 carbon chemicals. And I made the number into red to designate those chemicals that are already found in humans. So for the sulfonate, it will be C6 and C8, PFOS, PFOS, and PFHX. C6 sulfonates, and in the carboxylates, the C8, PFOA, the C9, and C10. Okay, so just a quick word, what are these chemicals, just so that we are all on the same page. These are synthetic, totally synthetic chemicals. They don't occur in naturally. They are very stable, non-reactive, and they only been produced for the last 60+ years, since the 50s. What makes them so unique is that they are both hydrophobic and oleophobic, meaning that they don't like water and they don't like oil, which make them an ideal surfactants. The most useful chemical, commercially useful for this of these chemicals are the C8, 8 carbon. So as I said, there are a whole range of this chemical, but the most useful is this 8 carbon chemical. That they are water resistance, oil resistance, and dirt resistance. But by 2002, the major manufacturer of this country, of PFOS in this country, by 3M, stopped the production because of public concern and some of the toxicological findings. And this is followed by DuPont in 2015. They also stopped production of PFOA, the carboxylates. So as I said, there are a lot of uses for this chemical. In fact, we don't really get, even at EPA, we don't really get a whole all the application of this chemical. And I just listed some of them. There are really hundreds of applications. They are typically used for fabric coating, carpet coating, because they are oil and water resistant. And they are very effective firefighting foam, which is the topic of the day. And I would just leave it there because the next couple talks after me would focus on that. So because of the concern of the C8 chemical, the manufacturer have come up with replacement for them. So for the sulfonate, we now have C4 sulfonate, PFBS, 4 carbon. And for the carboxylate, it's been replaced with C6, the hexanoic acid. Okay, so why should we care about these chemicals? Well, first of all, they're everywhere, and they are environmentally persistent. They're globally distributed. You can pretty much find it in the North Pole as well as South Pacific. They are detected in practically all environmental media that we know of. They are in water, air, house dust, soil, sediment, sludge from the wastewater treatment plant, and what is a bit of more concern is that they are not biodegradable in the environment, so they don't break down by itself. Now there are many of these chemicals have precursors in telomer alcohols or some of the amides and ethanols, but the terminal metabolite, when it can be metabolized in the body, but the terminal metabolites are the acid, the PFOS and PFOA, so on. So not only they're everywhere, they're already in our body and in the wildlife. And I listed a table of the latest finding in the body burden of humans and a couple of wildlife. So the production worker typically is in pretty high content, high amount in the blood. Now this is a serum level in parts per billion, because the workers work in the plant and they dip the hand in the barrel, and so their exposure is pretty high. But NHANES for the last 18 years, NHANES is a study conducted by CDC. It's a survey, national survey that represents our country. They have been checking this chemical for the past 18 years, and you can see the number listed. They report out every other year, and they've pretty much found 5 of these chemicals in across the board in our population. PFOS, PFOA, the 2 C8 chemicals, the C6-sulfonate, the C9 carboxylates, and the C10 carboxylates. And then you can actually, now you can, because of the follow-up by CDC, you can actually see a trend develop over time. When they first measure it, the level is very high for PFAS, but remember they stopped production of this chemical by 2002, so you can see the level dropping over time by almost like 75% or so, from 30 parts per billion to about 5. That is the most recent data coming out from NHANES for the 2013 to 2014 samples. P4 is sort of stay on a little bit longer, and I think by 2003, EPA has a consent agreement with the manufacturing facility to sort of tighten up the release of these chemicals to the environment. So by about 2009, 2010, you can see a drop of this chemical from about 4 to about 2. So enforcement action actually does work, and as I said, the chemical, even P4 has been withdrawn from the market in 2005. So perhaps in the next few years we will see a further drop. But on the other hand, the C6-sulfonate seems to be persistent pretty much over the year, from about 2 to about 1.5 over the year, and that is not really moving by too much. And I must say this chemical is also been associated with the AFFF mix. So this may be something that we should pay a little bit more attention. And C9 is again manufactured in a very small amount. That's why the level is very low. But it actually saw an increase of this chemical for the first few years of measurement, but it's also on the way dropping. And the C10 is a really latecomer. The level is even lower. So this is C10 most likely is the contamination in the manufacturing process. So there are a couple of well-known hotspots. Actually, there are more of them coming up now. One is in Landsberg, Germany, when the chemical containing PFOA is being dumped illegally, and you can see the level almost 10 times higher, or 10 times or higher. And another hotspot is in Little Hocking in West Virginia, in the West Virginia Ohio area, where there's a major manufacturing plant, and it's contaminated local area with drinking water, and the level is about 10 to 20 times higher than the national average. And you can actually see the signature. Well, P4, this is playing mostly big PFOA, so the other numbers are very close to the national numbers. And I want to also point out that it's just a couple examples of the wildlife. They are finding the lake trout, and the polar bear is always fascinating for me. How does it manage to go all the way to the North Pole? And there is very little information about that. So not only they are everywhere, they're in our body. Oh, one thing is that just a couple words about the exposure route. So as far as we know, there are 3 ways that it can get into our body. One is from food, especially seafood, fish, because this chemical are found in the water. But there also been shown that they can migrate from our food packaging paper. So for instance, your pizza box, your microwave popcorn bag that are also coated with this chemical. So when, and it's been demonstrated, they can actually migrate to the food that we eat. So that may be one way of a portal of entry. And as I said earlier, they are already found in drinking water, as Ms. Sullivan earlier addressed. In fact, that has drawn considerable attention of this chemical from the drinking water. Now, house dust is another issue, most likely from the application of this chemical to the fabric upholstery as well as carpet. And when we dust, and we are very diligent in dusting and vacuuming, essentially the chemical come off the carpet. So you also have a fairly high level of them in the house dust. So not only they're everywhere in our body, it turns out that they can hang around quite a bit. So typically, when you have chemical exposures, especially drugs, you want to have them in a body for maybe from hours to days. But for these chemicals, and I listed the table here, the half-life, meaning that if the time that takes the chemical, for half of the chemical to disappear, even though you don't take in another molecule. The time in human is exceedingly long. They can range from months to years. For instance, the C6 sulfonate can be like almost 9 years. This is really unheard of. Even the shorter chain chemical, they are days unto months, so that is quite a bit of concern. And lastly, not only they are everywhere in the body and hang around, they may be harmful. But I want to stress that the data from this point is mostly based on animal studies. And the caveat is that many of these toxicological studies are done with very high doses at the 2 to 3 order magnitude, and that's what detected in general population. But I must caution that sometimes they can drop down to about 2 orders or magnitude or even lower in the highly exposed population as well as the workers. And there are 5 major toxicity that's been reported: liver toxicity, developmental toxicity, tumor induction, immunotoxicity, 6 actually, hormone imbalance, and neurotoxicity. And I will go over this very quickly in the next few slides. But before I do that, I want to sort of point out 3 unique features of this chemical that would lend some understanding to the adverse effects in pharmacokinetics, how this chemical move around in the bodies, where do they go to, how long does it stay. Relative potency, this chemical, there are a whole bunch of them, as I said earlier. Are they all the same? Are they of varying potency? And not only the individual chemical, we know that there are many of these chemicals in the environment already, and there are many of at least 5 detected in the body. So we want to know how would they interact? I mean, rather than just one chemical at a time, do they add up? Are they synergistic? Or are they antagonistic? So the next few slides, I want to go over some of these features. So it turns out that not all PFAS are created equal. This is a big table and a lot of numbers, and this is the half-life estimates in a number of species, rodents, laboratory rodents, to monkeys, to humans. And I essentially segregate out the numbers in terms of a short half-life, intermediate half-life, and long half-life. So the green numbers are the short half-life. As you can see, we have 1, 2, 3, 7 of these chemicals pretty well studied, 3 carboxylate sulfonates and 4 carboxylates. So as you can see, the shorter chain, the chemical, the shorter the half-life. So C4 sulfonate, C4 carboxylate, C6 carboxylate, they are green numbers. So the half-life is in terms of hours. And as you move up the chain length, the half-life would get longer and longer. Okay, so the C9, for instance, the half-life is almost a month, to even in the laboratory rodents. And I want to point out one chemical, PFOA. If you look at the rat, there's a major gender difference. In the half-life in male rats is about 4 to 6 days. The female rats is only 2 to 4 hours. So it's huge difference. So when you read the literature, you have to pay attention what species the study is on. So you get a better idea. On the other hand, the mouse doesn't seem to be have that gender difference. Neither does human nor the monkeys that we can tell. But if you move up from the species in the animal or in the order from rodents to monkey to human, you can also see a trend that the human half-life is much longer than the monkey and than the rodents and other species. So these are very unique feature for that. Not too many chemicals follow this kind of profile. So I cannot advance. Too fast. So what about the potency? So given that they are being eliminated at different rates, it's very difficult to study the relative potency in whole animal, because then they are not really equal. So what Dr. Abbott on our team uses in vitro cell culture. In this case, the chemical just stay in the well, so there's no place to go. So in this case, you can actually compare everybody on the same platform. And that's what she did. So she actually looked at about 12 of this chemical. And again, you can see some kind of profile. So the longer chain carboxylates, the one that I labeled green, are the most potent. Now, the way to look at this data is how much chemical do you need to achieve certain activity. So the lower the number means that they're the strongest, because you don't need very much to achieve the same effect. So, for instance, PFNA is the strongest, most potent of all. You only need 5 micromolar to achieve the same effect. And they are about comparable to the C8, C9, and maybe C11 and so from C7 to C12, but C11 carboxylate are about the same. And in this case, actually, what Dr. Abbott did was compare the mouse plasmid versus in the human, so you can actually also do a comparison between species as well. And as you can see, the same long chain, the same profile long chain producing more potent effect is also seen in human. In that PFOA, PFNA, the C7 sulfonate are the most potent. But as you go further away, as a shorter chain, they become a little bit less potent. And in this endpoint, looking at a nuclear receptor called PPAR alpha, and I will say a little bit more about that a little bit later. For this unique endpoint, the carboxylates are much more potent than the sulfonate. As you see the bottom, they are all sulfonate, and they are much less potent, both in the mouse and in humans. So at least even with one endpoint, we can sort of do a little bit of comparison between these chemicals. So how about mixture? So what Dr. Abbott used is the same platform of the COS1 cell to look, and then you can where you can add the chemical in combination. So in this case, what she did was add PFOA with C6 sulfonate, C6 carboxylate, and C9 carboxylate, or C6 sulfonate, or the PFAS. And add them together and a ratio so that you can tell whether adding, say, does 1 plus 1 come out to be 2 or something like that. So if they are purely additive, and the results show that they are that is the case. So if you have synergistic effect, you will have like 1 plus 1 equal to 3. That will be synergistic. So she did that, and this is equimolar. So this is really 1 plus 1, whatever concentration. So she thought, well, but in the environment, not this chemical, not all these chemicals exist in 1-to-1 ratio. What happened if the ratios are variable, such as those shown by Anne Haynes? So what she did is she looked at the time 4 chemicals that have been detected in Haynes study, and used that ratio. So this is a variable ratio to see the combination. And in this case, actually, the effect was a little bit less than additivity. But so by and large, these chemicals, you can see them, you can add them together in terms of effects. At least they are not synergistic, so which is a little bit more troublesome to interpret the data. So just to quickly summarize the characteristic of PFAS effect is the clearance rate, the half-life, long chain is typically longer than the short chain. Half-life in human is much longer than the monkeys and the rodents. And there is, for some of the chemicals, there may be a little bit of gender difference in males. In the rat, for instance, much longer than the female. And in general, if you even in human, the males are very slightly longer than the female as well, but nothing like the rats. In terms of potency, they also vary based on chain length and the functional group. So the longer the chain length, they are more potent, and for this one endpoint that we look at, the carboxylates are much more potent than the sulfonate, and the potency in rodents seems to be a little bit more so than the human. And the mixture, as I said earlier, seems to be additive. So, okay, so now let's move on to quickly on the adverse effects. As I said, there are 6 classes of toxicity that that's been reported. Liver toxicity, hepatotoxicity, perhaps is the hallmark or adverse effect of this chemical. Pretty much every chemical we look at so far would cause enlargement of the liver, enlarged liver. If sufficient amount of this chemical would get into the body. So even for the short chain, which is less potent and clear faster, if you really give them a big dose, you would still see the enlarged liver. And in the more potent chemical, you don't need so much. So the comparative effect is the C12, C11, C10 are about the same equal potent. They are a little bit greater than C9, C8, and so on and so forth. Essentially, what happened with this enlarged liver is that they alter the lipid metabolism and trafficking of fat. In the rodent model, you have a little bit less serum blood cholesterol, and I would say a little bit more about that a little bit later, and as well as steroid metabolism. We also know a little bit now how these effects are being brought about, and this is sort of mediated by the PPAR alpha molecular pathway, which is what we use for the cell culture system. And these are the metabolic sensors. So this is a sensors in our body to figure out how much fat you have, what should you burn fat, should you store fat, and glucose, so on and so forth. So they essentially control our intermediary metabolism. And there are other molecular sensors as well, something called CAR, PXR. That may be also involved in the PFAS activity. But by a large effect, the liver effect, PPAR alpha is the most predominant one. And more recently, we also, from our own laboratory, we also have found that the exposure to this chemical would cause fatty liver. So essentially, there are a lot of fat in your liver. And there are PPAR alpha dependent and independent pathway, and this is really need to be worked out a little bit more. So developmental toxicity, our lab also spent a fair amount of time looking at this chemical. So the way we looked at it, the way the study was designed is that we gave the chemical throughout pregnancy, and then you look at the pregnancy outcome and see how successful is the parturition and the neonates. So there's very little birth defects per se prenatally when we looked at of this chemical. But if you let the animal give birth, they're all born alive. It's not that there are any problem with stillbirth. But in literally hours to a day or so at the very high doses, these are, I must also stress, these are very high doses, okay? The animal, the neonate, the offspring started to die, and they pretty much die. We can see a symptom of respiratory insufficiency. They are gasping for air and they turn gray and then just die in front of you. And this is totally dose dependent. So the higher the dose, the more animal will die. And you can say PFAS and PFOA, you see similar profile. And we are using a mouse model now, so we don't have to deal with the PK, the pharmacokinetic issue. Now, C9 PFNA, the profile, you see neonatal mortality, but it's a little bit different profile. I must also say that the C9 is a little bit quite a bit toxic, so you don't need as much dose as high a dose to see mortality, but the profile of death is a little bit shallower, so the animal die of a little bit slower death, almost like wasting away. On the other hand, PFBA is the C4 carbon chain carboxylate. We gave a huge dose, like 300 milligram per kilogram, and nobody dies. And partly because this chemical, remember the half-life of this chemical in the mouse are only hours. So essentially, there is not enough of this chemical accumulated in the body to really cause any damage. Also, not only PFBA, but PFBS or the C6 carboxylate, you don't see much of neonatal mortality as well. And in the bottom, I saw listed in the PFOA in the rats, you don't see any effect, again, because of the huge gender difference I told you a little bit earlier. in the rats, the female rats really also did not accumulate sufficient chemical to cause damage. And there are the other chemicals. They also been examined. The C12, C11 chemical. There are a little bit of the developmental toxicity is a bit different, but in the C12, C11. No, C12 carboxylate, you do see pregnancy loss, so maybe it's quite toxic. I mean, the animal didn't even make it through the pregnancy. So,
Dr. Lau, this is Rick here. We've only got a couple minutes left, and I was wondering if you could.
Okay, I will speed up a little bit. So only the neonatal mortality, there are effects on growth, delayed growth, and development. I'm having a little trouble advancing the slide. So induction tumors, with PFOA, there are 3 tumors in the rodent model: a liver tumor, pancreatic tumor, and testicular tumor. And this is called a tumor triad, or a signature for PPAR alpha pathway of causing tumor. As I said earlier, but on the other hand, I want to stress that as far as we know, the liver tumor induction by PPAR is quite unique to the rodents. So human can have tumor induction in the liver, but do not use the same molecular pathway as the rodent. So application of extrapolation of the rodent data to human is a little bit questionable. And there are other tumor in the fish that use a living mechanism, and PFOS has also caused liver tumor. But the other chemical that's been looked at, there is really no incidence of tumor reported. So immunotoxicity has drawn quite a bit of attention lately. So this chemical suppress the adaptive and as well as innate immunity. These are the system that we use to fight off foreign pathogens. So this is sort of acquired immune toxicity as well as innate fighting against infection and things like that. And again, there are evidence to show that they are mediated by PPAR dependent as well as independent pathway. But very recently they are also reporting in humans that PFOA and PFOS cause reduced immune response to vaccine in children, as well as increased prevalence of fever when the level of this chemical in the children is a bit higher. So there are a little bit of corroborating evidence between animal and human. Now, hormone imbalance, the major finding is that this chemical cause a reduction of thyroid hormone, but they are not your classical hypothyroid model because they don't activate the TSH response, which is a feedback pathway. So so far we still don't understand what is the health consequence of hypothyroxanemia, which is a term describing the reduction of thyroid hormone without change of TSH. There are some P4 has been shown to cause a reduction of testosterone and increase of estrogen. And in vitro, in cell culture model, this chemical has been shown as a weak activation of estrogen receptors. And these chemicals are perhaps a little bit more pronounced as an endocrine disruptor for the wildlife. So neurotoxicity is a little bit less well-defined. The data are quite inconsistent, but it has been shown in the cell culture as well as in whole animal. There are some deficits in terms of neuronal loss and cell death and behavioral deficits in animals exposed to these chemicals. But on the other hand, some of the other studies that used the EPA, the developmental toxicity guideline, they didn't find anything wrong with PFOS and C6 carboxylate. So I think this area needs to be a little bit better studied to see if there anything there. So I'm going to skip the summaries because I essentially just repeat myself. If I can advance the slide. So there are quickly, I just want to spend the next few slides on the human study. So especially in the last 10 years, there's a lot of study, epidemiological study with these chemicals. And they are, as I said earlier, the ENHANCE study conducted by CDC. And there are studies where they're highly exposed population, the CH study, and there are biomonitoring study with the production. So the exposure kind of goes up as you go down the slide. So some of the highlight finding is that in contrast to the animal model where you have decreased cholesterol in human, actually there's a pretty consistent report of increased cholesterol and uric acid in our body burden. So we don't really quite understand why it's such an opposite finding between animal model and human, but nevertheless, the finding in human are pretty consistent across different cohorts. In the CH study, there are incidents of testicular and kidney cancer, delayed onset puberty, which is also pretty consistent with the animal finding. Although preeclampsia is hypertension, hyperpressure during pregnancy, and this is quite unique in the human study that we haven't really seen that, or we actually haven't evaluated that the endpoint in the animal model. So the next slide I just essentially put together, and you can go back, you can read this carefully yourself, comparing to the concordance or discordance between animal study and human study. So for instance, the liver is still, this is where the difference is in this decreased cholesterol in an animal, but increase in human. Reproductive is, of course, we don't see any birth defect, and in human we don't see any neonatal mortality, thank goodness. But mostly because of the dose level. But on the other hand, we do see low birth weight, growth deficit in both animal and human at lower dose. Tumor, we've seen concordance in testicular cancer, and in human you see liver as well. Immune response, as I mentioned earlier, you see quite a bit of concordance between animal model and human. And endocrine disruption and neurotoxicity, especially neurotoxicity, there's very little good confirmed finding in human that we can look at. So in the last slide, what I want to sort of put out there is this not easy risk assessment for the regulatory agency, mostly because of these points. There are many of these chemicals in the environment, and not only these are PFAS, there are only about like 20 of these around. But there are over 2,000 of the perfluoroalkyl substances. They are all of all sorts of chemical structures out there where we don't even know what they are, how much are there, and of course very little toxicological data. So this is clearly an emerging area, as Sullivan mentioned, that for us to look at maybe some little high throughput assay that really we can screen a lot of these chemicals. There are a large difference just for the PFAS body burden between animal and human. As you can see, the half-life is very tremendously different, and we have no clue what is the underlying mechanism for that. There are differences in mode of action. I mean, we only know PPAR alpha as one of the major mechanisms, but there are clearly others that we are, in fact, they are emerging. And once we know a little bit better, we can actually get a better handle for extrapolation of the animal data to humans. For instance, some of them are actually, as I showed earlier, the rodent data are not relevant to human, such as the liver tumor between mice and human, because humans do not use that molecular pathway. Of course, there are different endpoints with different dose response with different endpoints. So which one do you pick? Which one is the most sensitive to use for risk assessment? And the epi data can only show association. So essentially, you rank order the chemical in the body burden, and you see whether the higher the higher the chemical, the more health effect that you see. So, but there's it's kind of no causality. You don't know exactly whether it's true that this chemical does cause this adverse effect. So, but having some biological understanding using the animal model may help to reduce some of these uncertainties. And I think that's all I have. I'm sorry to go over a little bit. So I'll be happy to entertain any questions.
Dr. Lau, we've got several questions. What I'll do is we'll either have them at the end of the webinar, or I'll send them to you offline and get the people's email address to route the answers to them. So,
either way is fine. I can stay until the end of the webinar to answer some really important questions.
Okay. Yeah, we've got a few, but we need to move on to our next speaker.
Okay.
Okay.
Let me pass the ball.
Okay. Our third speaker is Bill DiGiuseppe. As I mentioned earlier, Mr. DiGiuseppe was heavily involved in getting this webinar organized. Mr. DiGiuseppe is a principal hydrogeologist and program technology manager with almost 30 years of experience in soil and groundwater investigation and remediation sites. He is a licensed professional geologist and leads CH2M's Chemicals and Issues Emerging Concern Community of Practice. Mr. DiGiuseppe has led large and complex environmental investigation and remediation projects, published technical articles, chaired sessions at international conferences, and co-authored a definitive book on 1,4-dioxane with Tom Moore. At this time, I turn it over to Mr. DiGiuseppe.
Okay, thank you, Rick. I appreciate everybody's time, and I'll be talking, sort of defining the problem a little bit in a broader sense rather than the detailed toxicologic information that Dr. Lau presented. So we've talked a little bit about where these things come from in a variety of different consumer products and other things. The focus, obviously, on this SAME webinar is on aqueous film-forming foam. You know, I would say one of the important things is that even in the EPA's derivation of that health advisory, they assume that 80% of the body burden of perfluorinated compounds comes from other consumer products in one's world, and Dr. Lau's evidence of impacts to people, I think, supports that, not necessarily tied to specific sites. But the aqueous film-forming foam is an important issue, and there are a number of different ways that was manufactured over time, and so there's different compounds that might be involved depending on the era of usage and the products used. The only other thing I'd like to mention, the chrome plating mist suppressants is kind of an interesting one that's been brought up as a potential source of PFOS, and that's a very specific application. Emissions controls and regulations related to chromium plating came in the early 1990s and mid-1990s, and so the foam blanket was allowable if you had decorative chrome as opposed to hard chrome plating, like for gears and industrial parts. So it's a very specific application, and I think a blanket caution about if you had chrome plating shop, you must have had impacts that might not really be correct. Needs to be looked into in more detail. In terms of storage of AFFF and sort of the distribution in our society in the U.S., you know, as Ms. Sullivan mentioned, there's a considerable quantity within the U.S. military, but there is a much greater quantity elsewhere throughout our society, and this is actually old data, and a fair amount of this may be outdated, but it does give an indication of how widespread the AFFF potential storage and releases might have been. So it's something to think about. And Ms. Sullivan also mentioned the alternatives to foams and the Air Force's efforts to find fluorine-free foams or to help develop those. And I apologize, there was an image here, but it was actually a video. That's probably why it got stripped out by PDF, and I didn't intend to show the video. But if you want to look online on YouTube, you can see the lack of effectiveness or marginal effectiveness of fluorine-free foams as they currently exist. They're really not tremendously effective, and so more development is needed. They don't currently meet the mil spec as well. So, and then the other thing is some of these replacement foams have a much higher quantity of other detergents and surfactants and other things. So they're not necessarily non-ecologically impacting. They just may not have the fluorine in them. So I think as we go forward, handling AFFF usage as a release of a potentially hazardous compound is the best way, and there are some states that have guidelines for capture and cleanup of that material as it's used, as opposed to just washing it down into a stream where that biological oxygen demand could have a substantial load. Related to occurrence, in the U.S., a lot of the information has come to light in the last couple of years and has hit the press and everything related to drinking water, and that was driven by the Safe Drinking Water Act Unregulated Contaminant Monitoring Rule list that came out in 2012, where EPA was assessing sort of how big of a problem are these compounds, and these 6 compounds were required to be sampled in drinking water supplies servicing populations greater than 10,000 people. This figure is from a recent publication, and it's a little bit misleading, but it is showing the locations of the drinking water occurrences of PFASs, but these are by hydrologic basin, so this is a basin or a water supply that has at least one impacted well within it. But it does kind of show the distribution in the dominantly the industrial portions of the U.S., but there are some other factors that affect where these show up as well. And then specifically PFOS, perfluorooctane sulfonate, as of January 2016 data, had a detection rate of under 1%, which is not necessarily a problem on the surface, and especially compared to, for instance, 1,4-dioxane, which had a detection rate of over 10% in our drinking water. But it does typically indicate that there's some sort of an impact up gradient, and a lot of that has led to various water utilities looking upstream to identify where that source might be. And then the other thing that this is just figure showing is the different advisory levels or guidance levels, and the change from the 2009 advisory level for PFOS down to the May 19, 2016 level, which then makes more of the results be exceedances. And then some states like Vermont actually has a cleanup standard that's even lower for PFOS or PFOA, or there's some. And that is a trend going forward, and I'll get to that in a minute. From the chemistry standpoint, Dr. Lau went into this a little bit, and I'm not going to go into it in tremendous detail because it is complex. This is the number of parameters and classes or compounds and classes that Jennifer Field's lab at Oregon State was able to detect as of about a year ago, and it's already out of date almost by a factor of 2. She said she's up to about 200 or 250 compounds. And as Dr. Lau mentioned, we don't have toxicology information for many of these, so it's kind of a question of what's the value of understanding or knowing this. And one of the key elements to these compounds is that they can biotransform from one compound to another. And so understanding what all the other material is that's there, these precursor compounds, is as important as understanding what the PFOS, PFOA, or other specific compounds are. And here's an example, kind of a little sort of simple conceptual site model related to some of these compounds. You can have a complex molecule that might be hung up in the soil at a release location, might not be migratory, but that can biotransform either directly or through intermediate products to form the PFOS or PFOA. In this case, the parent product is this fluorotelomere thioamidosulfonate, which you can see some sort of common elements, the carbon-fluorine chain on the left and the sulfonate on the right, but that can degrade through fluorotelomere sulfonate step and end up at a carboxylate in this case. But that's something to consider in assessing the extent of impacts, is that those compounds many of them are hung up in the source area, not necessarily the PFOS, PFOA, but certainly some of these precursors might be there. Whoops. There we go. Some analytical considerations. Some of this has been touched on a little bit, but the standard method is EPA method 537. There's also a ISO method that's comparable. These are liquid chromatography tandem mass spec methods. It's an expensive piece of equipment, and not all labs offer this, but there are a number of labs accredited worldwide, and especially in the U.S., the DoD E-Lab program. You can go online to the DENIX website and see which labs are certified for which methods. And method 537 is a drinking water method, so in order to do groundwater or leachate or soils or sediment or other things, that labs have to modify that method and get a separate certification. I would note this Jupiter lab was added on here. They're not on the DENIX website yet, but they've received the letter stating that they are accredited now. So it is a handful of labs. It's not necessarily every facility that has these, and as Ms. Sullivan mentioned, there's been capacity issues this year as a lot of work has been done, particularly by the DoD moving forward. So there's a little bit of overwhelmedness in the labs, but more labs are coming online to offer this service as well. And prices have come down dramatically in the last year or two because of that. One of the issues, again, that Ms. Sullivan alluded to, this EPA technical memorandum that just came out in the last month, is related to branched versus linear isomers of these compounds. We typically show them as a chain, a linear chain of carbons with the fluorines attached, but they can, in fact, form a branched version of that. And the issue comes up with how the labs are calibrating. If a calibration solution is a purely linear solution and you only look for those peaks, and then sample a field sample, an analytical sample, you may miss the branched compounds that are present because both are present in the environment and in the AFFF solutions. And the results could be off by a substantial amount. So that technical memorandum made recommendations on how the lab should do that. And I think over time we'll see evolution of those analytical methods as other issues come up. So principally the issue is that when we do the method 537, we're only detecting a subset of those compounds. It's somewhere between 16, I think, is in the official method, but some labs are offering up to 20, 25 compounds. But as I mentioned, academic labs can often get into the several hundreds. So one of the, and that group of compounds that we're not seeing, some of those are precursors. So it's important that we understand what that total fluorine load is, or those precursors, so that we can see what, through biotransformation or remediation, what else might occur, what compounds might show up. So there is no standard method for assessing those precursors. The total oxidizable precursor assay that was developed at UC Berkeley is a really good tool. It takes a sample, runs the 537 more or less, then oxidizes it and transforms some of those compounds, and then runs the 537 analysis again so that you see what it was that you missed that was a precursor to one of those compounds that are detectable. Other approaches are looking at total organic fluorine or absorbable organic fluorine, a couple methods to do that, but kind of looking at the total fluorine load rather than just individual compounds to get an idea of what else might be present that you're not seeing. One approach to this could be using field screening tools. We know that these compounds have very low health advisories, the 70 nanogram per liter sort of number, but the total fluorine load for a site might in fact be in the part per billion range, or maybe up to 5 or 10 part per billion. We've done some testing with a couple of these types of tools, and we've gotten down to around 10 micrograms per liter pretty reliably on a detection limit, and we're working on driving that further through concentrating the samples. But if we can get that down to a 1 microgram per liter level, then that could be a field test kit to sort of quickly assess a site's impacts and decide where the sampling should be focused. So then some additional field sampling characterizations. Sampling interferences are certainly going to be a problem or an issue. We use, in our industry, we use a lot of water repellent and stain repellent and various compounds. A lot of the materials that our sampling equipment are made of may in fact have fluorotelomers, fluoropolymers, things like Viton is an example of that. So seals and impellers and things like that may be impacted. So we did a sampling study a little while ago where we essentially ran deionized water through some of the most common sampling equipment, and Jennifer Field's lab at Oregon did the analytical work to look at what might be present sort of coming off of that sample equipment. And these are the results of that study. And the red dots or boxes represent the 6 UCMR3 compounds. The grayed out ones are other compounds that Dr. Field detected in her lab. And you can see there are some impacts. We had a peristaltic pump with polytetrafluoroethylene tubing, and you know, just to clarify, Teflon is an example of a polytetrafluoroethylene product, but this was not a Teflon branded product. It was sort of an off-brand, you know, that you might order. And we did see some impacts from some of those compounds. So it's particularly important that we pay attention to that material that we're sampling with to ensure that we're getting the right material and we're not introducing anything. And then to take that a little step further, we're working right now with Hope College and Oregon State University doing an assessment of a number of other pieces of field sampling supplies and equipment. So we're looking at notebooks and notepads and Post-it notes and markers and tape and all kinds of things that we use in the field to see what might contain fluorine that we might ought to be paying attention to. And there are some things that are kind of surprising in there. There are others, there's some urban legend that we would like to diffuse actually as well, because for instance, everybody says don't use Write in the Rain notebooks because they have a water repellent coating on the paper. Well, it turns out there's no fluorine whatsoever in that coating. That is a silicon-based water repellency, and therefore Write in the Rain notebooks are likely okay. And so rather than trying to avoid these things based on hearsay, we're doing a project to assess that. So those results are going to be, the total organic fluorine's been done. They're now, all that material is headed over to Oregon State University to run the full LCMS-MS analysis, and that'll be published at some point in 2017. A couple regulatory considerations we've alluded to or mentioned, some about the health advisories. All the way on the left is the EPA lifetime health advisory level of 70 nanogram per liter. That's a summation of PFOS plus PFOA because of the expected sort of mode of action and impacts on various organs. Other states have a variety of different standards, some lower, some higher. Some of them are based on the summation, some are individual compounds, and they're kind of constantly changing. You can see most of these came into being just in the last couple of years. And then that, while it's not formal, some states, how they're applying the various guidance levels is changing over time. So for instance, in Colorado, recently CDPHE suggested that in addition to PFOA and PFOS, that the PFHPA, the C7 compound, should be added to that 70 nanogram threshold related to a site in Colorado. So that's a constantly evolving arena, and undoubtedly what the likely future trend is more states having guidelines or regulations and more compounds being within that list. And perhaps we should be heading towards a total fluorinated number or something like that as we learn more. And then internationally, you can see just for comparison, the levels are generally pretty low, and even the concept of summing the perfluorinated compounds, for instance, in Sweden, they have a level of 90 nanograms per liter, but it's the sum of PFOS, PFOA, and these other 7. So again, those are, many of them are fairly recent, some of them this year, and those are getting more strict over time overall. A couple other characterization sort of sampling considerations. One of them, you're not intended to be able to read this. This is after a poster that we did a couple years ago, and really it's just emphasizing the thought process that should go into deciding how likely you are to have an impact at a facility. And for instance, I mean, one element in here is the chrome plating, because we had been getting indications from regulators that if you had a chrome plating shop, you have to sample for it because you must have used the foam blanket. But in fact, a lot of DoD chrome plating shops, maybe you stopped chrome plating in the 60s prior to the imposition of those emission standards, and so it's a very low likelihood of that having been present. So just the recommendation that it be a very intelligent, thoughtful process of how likely you are to be impacted, as opposed to a knee-jerk sort of reaction to certain things that you might have heard. And one last set of concepts. So we're in assessing sites and things, we're looking for different tools to kind of make it easier to evaluate potential impacts. And or treatment capabilities, and I know Jeff Burdick's about to talk, and Ian Ross about treatment technologies, but in this case, this is a carbon treatment plant where we have plant effluent, influent and effluent samples, and this is just a radar plot kind of allowing you at a glance to see how effective that plant is on which compounds. But beyond that, this is a series of the plant effluent in the upper left, and then a series of residential wells. This was a location where the site had previously been infiltrating treated water from that carbon, but not monitoring for perfluorinated compounds necessarily. And you can see that in the top row, the signature of the various residential wells matches the plant effluent signature in terms of being PFOA and PFH excess heavy, whereas the wells on the bottom have unusual patterns that don't really match and sort of don't look like the same population of water. And as it turns out, the two upper wells are in the flow paths from the injection point of that effluent water, and the other three wells down below, one of them is up gradient and two of them are side gradient far enough to be unimpacted. And I think what this really emphasizes is that the compounds that are present in a residential setting, when one residential well might be actually drinking the water that a septic field from the upstream residential well might have been discharging, might have a signature of those consumer products much more so than of the AFFF. So in this case, it's a fairly clear indication that those three lower wells are not impacted by the injection of the water, but are impacted from consumer products. And so that's a complication that we all are going to need to think about as we move forward. So I appreciate everybody's time. I kind of zipped through that, and really it was just a smattering of characterization-related topics, but I hope everybody found that useful. Rick?
Okay, thank you. Just taking off mute here. So we have a question that was submitted before during Dr. Lau's presentation, and the question had to do, since you raised it in your presentation, Bill, is there a concern with the fluorocarbon coatings of medical tubing?
And I don't have a specific answer or knowledge, but I would say that that is a consideration. Some of these products do leach perfluorinated compounds. We've got evidence of that. And again, to give DuPont Teflon credit, they have reformulated their products away from the C8 compounds, so it's not a concern for DuPont Teflon branded materials, but others might in fact have those materials. And it's a concern in the analytical lab as well, obviously. A lot of Teflon products or water and grease repellent products in there.
Okay, very good. Okay, we do have a few more questions, but we'll push them to the very end of the webinar so we can stay on track with the schedule here. Thank you, Bill. Our final speaker is Jeff Burdick. Mr. Burdick is the U.S. Director for the Industrial Sector within Arcadis Corporate Technical Knowledge and Innovation Group. Mr. Burdick has also served as the U.S. Director of the Remediation Strategies Discipline and is active within the aerobic bioremediation, anaerobic biooxidation, and chemical oxidation subdiscipline teams. Mr. Burdick recently finished 6 years as the Remedial Technical Director for Arcadis European Operations. There he led the remedial investigation and remedial design efforts at a large perfluorinated compound manufacturing facility near Antwerp, Belgium. He is a part of a 20-person team of Arcadians involved in PFC projects in 8 countries. At this point, Jeff?
Thanks. So first off, I'd like to thank the organizers. We appreciate the opportunity to talk in this forum, and I'd also like to thank the other panelists for helping us to set the stage here. I'm sitting in Philadelphia with Jeff McDonough, and both of us will be presenting overviews both on some of the known or standard remedial technologies being applied to perfluorinated compounds, as well as some emerging technologies. However, before we do that, we're going to hand the ball off to Ian Ross in the UK. He's going to talk about a little bit more depth in terms of PFAS chemistry and specifically considerations that we need to take into account when we're developing a site conceptual model and setting the stage for treatment technology evaluation. Ian?
Thanks, Jeff. So we've come across the term perfluorinated compound, and I wanted to start by showing what they are and talk about the remediation criteria or things to be considered when you think about perfluorinated compounds. So perfluorinated compounds, the per means that the carbon on this chain is completely saturated with fluorine, and it can therefore be various chain lengths, with the octanoate being the one that's currently of concern for PFOS with a sulfonated group, or for PFOA This chain here is 7 long with a carbon on the end. From a remediation perspective, these compounds are totally recalcitrant to biodegradation so far. They're pretty bulletproof, and they're classified as perfluoroalkyl acids, so another acronym for you, and that covers the full range, which normally what we're looking at is C4 to C12. So PFAS as a term considers polyfluorinated compounds as well. Now these are compounds where you don't have a complete saturation of your perfluoroalkyl chain. You also have carbons somewhere on the molecule that are bonded to hydrogens. So polyfluorinated compounds, as an example, you've got a fluorotelomere alcohol at the top here. Now when that is volatile and evaporates into the atmosphere, UV can make that form PFOA, or it can form by biological action. So you have molecules that are not PFOA, but can potentially form PFOA. And that happens quickly in the groundwater when it's aerobic, but much slower when it's anaerobic. So the fluorotelomere unit here, when we talk about fluorotelomeres, they are perfluoroalkyl chains linked to this ethyl unit before you have some kind of functional group on it. And they're the simplest form of precursors in some ways. But you also have precursors which are cationic, and that means they stick to soil. So if there's an amino group there, they'll stick to soil more by ion exchange, so they're less mobile. And then zwitterionic as well can have both charges, meaning they're also less mobile. So they'll stay potentially in the source area by ion exchange for longer. So in terms of polyfluorinated compounds, there are potentially several thousand of them out there, with around 300 generally found so far in AFFF. If we look at the outflow of some water treatment plants that have been tested for known and unknown precursors, by unknown precursors, they've not been identified, but they're known to be there as a result of using the top assay, which is what Bill was discussing. You'll find there's quite a large proportion of the water coming out of POTWs going into surface waters here that are actually comprising unknown precursors. So there's lots more contaminant mass, which may factor into your remediation thinking, especially if you've got carbon usage and that sort of thing to consider. So to sum all this up, we've got a number of potential sources of PFAS, and they biotransform to form these perfluoroalkyl acids as dead-end daughter products that are likely to be on the planet over geological time, as there's not much evidence at all that they're going to biodegrade. So the rate at which this occurs, though, is going to depend upon the dominant geochemical condition. So if it's aerobic, you'll have faster breakdown to the perfluoroalkyl acids. And there's a huge number of these precursors out there that may stay in the source area. So to sum this up, we've got a conceptual site model of an AFFF release at a fire training area. So the shorter chain perfluoroalkyl acids are more mobile. They're more soluble in water. They pass through carbon faster, and they move faster in aquifer systems as they don't bind to the fraction of organic carbon as much as their C8 cousins. So in a source area, dominantly because fires have been put out, you have some kind of hydrocarbon L-NAPL there, and conditions are anaerobic, which would generally mean that precursor biotransformation is minimized. And if you've got cationic or zwitterionic precursors, they may stick to the soil much more and stay there as a continuing source. But many components of firefighting foams are anionic as well, so they could also potentially move away. And once they move out of what would be a short hydrocarbon plume in comparison, there's potential for aerobic conditions to dominate and then to become a source of the various chain length perfluoroalkyl acids. So we have more of a complex situation where we don't just have PFOS, PFOA, which are mobile and will move away from a source area. You also have things that could stay there and remain as a continuing source. In an analogous way to NAPL itself, you have this hidden mass, which will potentially make more of the contaminants of concern. So just focusing back on PFOS and PFOA, you look at physicochemical parameters. They're highly soluble. Solubility of PFOA with 3.4 to 9.5 grams per litre, with PFOS being about 520. They're not particularly volatile, They don't particularly partition into the air, and they don't sorb to aquifer matrices very significantly. And because they're anionic, they tend to repel from most aquifer formations like clays. But because of their extreme recalcitrance as well as their mobility, they can form some very long plumes, with plumes in Europe measured so far at 40 miles as a maximum. So really, we'll just hand over to Jeff to go through the water treatment.
Okay, thanks, Ian. So coming out of a pre-design or a PFAS-related pre-design, hopefully our CSM will have done a check on the PFAS chemistry, get an understanding of the fingerprint, maybe include a check towards precursors just so we get an idea of that precursor load so that we understand the longevity of the treatment that we might be getting pulled into and also how robust that treatment needs to be. As you'll see from some of these next examples, it's really important to also get an idea of site geochemistry, just basic background geochemistry, but also the presence of other constituents, because this really can help us screen and eliminate some water treatment technologies. And then also, with any groundwater treatment, we really want to come out of the CSM understanding our mass flux. So this slide really just gives kind of the big picture, an overview of technologies, and as Ian indicated and our other speakers have indicated, biological pathways or biodegradation methods are really not applicable here. We can have transformation of precursors, but really no transformation of our PFAS or C8 targets. Phyto is generally not going to work due to the volatility of these compounds or lack of, and air-sparge SVE, if anything, it might sweeten the PFAS or C8 concentrations in the subsurface. Ex situ thermal is a proven technique, but in situ thermal technique is generally not considered practical because we basically have to completely desiccate the subsurface. So really the crux of this talk is on groundwater extraction ex situ treatment methods. That is, there's some presumptive remedies being applied or evaluated on lots of sites. And then a few things at the bottom here, oxidation reduction pathways have shown some promise, haven't been proven at the field. And one comment on PRBs, since we know granular activated carbon works pretty well in removing C8 in large chains, it could be feasible to apply a GAC-based PRB pending the mass flux depths and that GAC change-out frequency. So this slide is from the Water Research Foundation paper that came out by Dickinson and Higgins this past May. It's a great reference, a great resource. I would urge everyone to give a look, give you some good background on water treatment. So when you look at this graph, basically the things on the left-hand side of the page are conventional drinking water treatment technologies, disinfection technologies, and basically if it's red, it means little to no removal of these perfluorinated compounds listed on the left-hand side of the page. When we move to the right side of the page, that's the remedies we're going to focus on. Granular activated carbon, anion exchange in resins, nanofiltration, and reverse osmosis. I will point out that the anion exchange columns, there's definitely some debate in terms of which of those cells could be colored, which colors, because there's a lot of different resins out there with specificity. So we wanted to put one slide in here about deployment in the field, because all these ex situ techniques that we're talking about are really the presumptive solutions for removing the PFAS. What will become a bigger and bigger factor here, and really a factor towards O&M and the burden of these systems, is municipal fees, meaning when we dump water to the POTW or discharge under a NIPDES permit, we can have fees associated with purely just dumping water that we've already cleaned. And those fees can be significant. And if you look here on an annual basis, you know, a 25 to 100 GPM system, that could be an extra $200,000 in O&M just related to discharging your clean water. So one of the strategies that we've deployed is using groundwater recirculation or directed groundwater recirculation. And this presents an opportunity for us to basically form a closed loop or a semi-closed loop such that we're minimizing the water we're dumping, but we also take advantage of some hydrogeologic principles such that we're going to flush the aquifer and we're going to flush the source to access that mass quicker, which could shorten our overall life cycle. One word of caution is if we do have to discharge some of the water, just be real careful what that fingerprint of the water is in terms of other emerging contaminants and what we could get pulled into. And also definitely screen for iron, because high dissolved iron can be a real challenge for this technique. So we're going to talk about GAC first. This is a presumptive remedy that many/most of our PFAS groundwater treatment scenarios are evaluating first. It is effective at removing PFAS and PFOA with some high removal percentages, and particularly effective at removing longer chain or heavier perfluorinated compounds. One thing to keep in mind is there is going to be competition, especially with natural organic matter, but also other perfluorinated compounds, precursors, and especially other contaminants. To give you an idea, GAC is about 80% less absorptive for PFAS versus BTEX. So a little bit of BTEX associated with a fire training area can really make your GAC costs go up. So when we're thinking about O&M here, you know, we mentioned saving some money by recirculating groundwater. Another thing that you can do, if we use reactivated GAC as opposed to completely paying for the complete incineration of the GAC, we lose a little bit of the absorptive capacity, but we can save about 15% on that GAC. Another advantage of GAC-based systems is they're fast. You know, we can go from rapid column testing to develop isotherms to construction of a couple million gallon per day system in about 3 months. And I would say the sweet spot of this technology is really end of the pipe diffuse C8 in groundwater. Next. This is an example from the Water Research Foundation paper, and this just looks at breakthrough of PFBA, PFOA, and PFAS on a lead-lag GAC configuration. So the green lines represent when the lead vessel was changed out, and the orange line is when both vessels or the final vessel was changed out. And what you see on the left, the climbing trend there, is PFBA. So PFBA has almost immediate breakthrough in the effluent. We see that breakthrough within a few months, whereas PFAS takes about 1.5 years or 7 to 8 months for PFOA to break through. Where we see that PFBA concentration kind of stabilize in the middle of the page, it's really, we now have desorption and competition with these other perfluorinated larger compounds that are easily adsorbed. So it's something to keep in mind. You know, we don't have PFBA as a regulated target. We don't view it as a health issue, but that is one limitation of GAC, in that it's going to be a little harder to remove these shorter chain compounds. We can accommodate for that with a little more capital up front, meaning larger vessels, longer empty bed contact time, and that can help us get better removal of those compounds. Ion exchange, these are acrylic or polystyrene-based resins that can remove the perfluorinated compounds using ion exchange, or sometimes the hydrophobicity of the resin versus the target. Usually a little bit more expensive than GAC, but there is a place definitely for resins given the specificity and really the range of different resins that are available out there now. Historically, the conventional wisdom was that resin technology would work much better for sulfonates than carboxylates, or PFAS more so than PFOA. However, there's now a broad range of resins available that have different chain length specificity, can remove both CA, PFAS, and PFOA very well, and at competitive costs versus GAC. There's also some specific resins that could be used towards shorter chain compounds like PFBA. So we see that as a potential bolt-on possibility here, meaning design a GAC-based system really focusing on regulated CA compounds, but down the road, if we need to add a resin to that treatment train to affect a new compound that's being regulated, that's something we could do and add in pretty easily. As is with most of these techniques, we have to watch groundwater chemistry, and we need a good check on that before we go in. Chloride and sulfates can hinder the absorption of many of these resins, as could high TDS. So pre-design really needs to look specifically at these different types of resins with site water. So RO, or reverse osmosis and nanofiltration, are both membrane technologies. Nanofiltration uses pore sizes that are slightly bigger than reverse osmosis, and what we're doing with RO is we're basically reversing the normal osmotic direction of solute transport in the reverse direction, and we're doing it at high pressures typically. High pressures for large municipal or large water treatment, and there is point of entry systems that can be used for RO and nanofiltration, basically small systems. U.S. military also uses these and deploys them for remote field applications with our troops. The main difference between a large and small system is we can get a lot of rejectate with a small system where there's low pressures, about a 5-to-1 ratio. A big cost consideration here, generally these are the Cadillac treatment options. Most robust, can treat every chain length, every compound in that perfluorinated realm, but the design is much more complicated because of the susceptibility for fouling. These are expensive pumps, expensive membranes, and so we need to keep them very clean. And we have to add pre-treatment to remove things like natural organic matter, TDS, particulates. We have to inhibit microbial growth and flock scaling inhibitors, and sometimes acids to lower the carbonate alkalinity. So all of this requires a lot more robust design and potentially a trickier treatment train that's going to add costs. And when we do get into O&M mode, both techniques require very consistent operating conditions, meaning as that filter or that membrane, the permeability starts to change during operation from little bits of fouling and preferential pathways, we need to toggle the flow and the pressure to maintain those constant cross-flow velocity and conditions to get good treatment. And lastly, there's some flocculation and precipitating agents out there. These are cellulose-based polymers. They have specific PFAS binding capacity capabilities, and we view this as really a good thing for the treatment train, or a good thing in our arsenal when we're near a source or when we have high C8 loading. We can basically add this via an EQ tank, 1 to 3 of them depending on the flow rate, and we can knock down that PFAS prior to the GAC such that we're minimizing the stress on the GAC changeouts, the GAC O&M. And this is something you could bolt on to your system maybe for the first year or two of operation until you start to knock that mass down, and it'll definitely make your overall O&M cheaper. Next, Jeff.
So Jeff Burdick talked about a lot of the technologies that are actually being implemented in the field right now. I'm going to talk about 6 different technologies that have promise or are destructive techniques that have been demonstrated either at the lab scale or have niche-specific applications. The first is senolysis. Senolysis is ultrasonic radiation that creates cavitation through collapsing and colliding of bubbles. That cavitation can result in extremely high temperatures at the surface area of the bubble, and when the PFAS would adsorb to that bubble, there would be a thermal destruction, so pyrolysis, decomposition. The data in the laboratory suggests that it's successful in high concentrations. It was treated down to about 10,000 nanograms per liter. In comparison to the standards that Bill was presenting, that's pretty high. So its applicability might be for high concentration waste streams, or maybe even the concentrated rejects from the technologies that Jeff was discussing. Some of the limitations associated with it is that it generally requires some specialized equipment and skill. It hasn't been demonstrated at the field scale yet, as far as I'm aware of in the literature. And with lower concentrations and higher flows, typical of the municipal systems that this would be applicable at, the energy costs can be appreciable. Some competition for it would be if you have high concentrations of volatile organic compounds or a really firm buffering capacity with high alkalinity, and that could be limiters as well. We're teaming with some academic institutions to further explore this technology and apply it as sort of a treatment train application. The next is proprietary stabilizing agents. So this is not for water just yet. There's plans to make it for water, but it's not there quite yet. This would be combinations of granular activated carbon, aluminum hydroxide, kaolinite, strength stabilizers, and other proprietary additives to decrease the leaching of PFOA and PFAS in particular is what the data has showed, but to reduce leaching to groundwater. Typical with in-situ soil stabilization techniques, you'd target an area, maybe a known release area, and essentially make a mixed monolith that is then stabilized or solidified with Portland cement and one of these stabilizing agents. Now, the limitation associated with this is that the PFAS don't degrade, so you're leaving them in place for a long period of time. And the aggressive leaching testing that has been done, and there has been some, has been with either the toxic characteristic leaching procedure or the synthetic precipitation leaching procedure, both of which are acidic-based leaching approaches. And so with the PFAS chemistry, it can absorb better under acidic conditions. So technically, if we wanted to do a more aggressive leach looking at this, we'd probably want to look at more circumneutral to alkaline conditions. Synthesized polymers, the next one, these are kind of exciting. They're relevant to contaminants, and we have it contaminants here instead of PFAS, because really the only data available was for PFOA, and it was pretty strong for PFOA, but we're teaming with vendors right now to try and test out some experimental regenerations and absorptive techniques. The conventional thinking is that it's effective for compounds that have octanol water partitioning coefficients that are greater than 2.5, and many of the PFAS have greater than 4. So the thinking there is that it's relevant. We just need proof of concept and to demonstrate it. And the regeneration of these polymers right now is not appropriate. The temperature is far too low, about 100 degrees C. We're teaming to look at some methanol-based extractions, which could be a little bit more cost-effective. So promising technology, but not quite there yet. The next two are related to electrochemistry. So this is electrocoagulation, a technology that's been around for a long time in the mining industry and the municipal water treatment industry. It's basically using electrical current to precipitate metal hydroxide flux, and then the PFAS and PFOA will absorb to that floc. And in laboratory tests, zinc has outperformed aluminum and magnesium flux for PFAS and PFOA with pretty rapid kinetics. One of the nice things about this is that you can manage the waste, which is the spent floc, by acidifying it and recovering the PFAS, but then you have a really concentrated source of PFAS that you need to deal with. So you're going to have some sort of treatment train. It's not a destructive technique. The concentrations that the laboratory have treated down to are, again, several orders of magnitude above the house. So this might be a treatment train type approach. Similar with Senolysis, the lower the concentrations, the higher the energy use to make this work. And ultimately, with the site-specific water chemistry, you could have of competitive binding. So could be promising, but again, needs some larger scale consideration for field. The next is electrochemical degradation. So this is a destructive technique like senolysis. It's direct electron transferred from the surface of the anode. It was confirmed in laboratory studies with fluorine mass balance, which is always a good sign of defluorination is occurring in both spiked water and groundwater. So looking at some of the competitive limitations, this has been a little bit more flushed out from that perspective. One of the secondary concerns associated with this technology is that if you do have reduced species such as chloride in the water that you're pulling out of the ground, which is typically available from 10 to 100 milligrams per liter, potentially thousands in brackish conditions, you can generate secondary problems like perchlorate. So that's something to look out for, and the acidity associated with the anodes can facilitate absorption. So that's something that you need to have a plan in place to account for that. The last one that I'm going to talk about before handing it back to Dr. Ross is aqueated electrons, or solvated electrons created through UV photolysis of iodine and sulfide solutions. This is pretty interesting because it's going to be very difficult to account for oxygen and nitrate, which would greatly or quickly scavenge this very reactive aqueated electron with a really low reducing potential. But it was confirmed in the lab scale, and I think the chemical reduction aspect here has a lot of applicability if they can find a way to commercialize UV photolysis to a way where we can generate these electrons at meaningful concentrations.
So in terms of chemical oxidation and reduction of these compounds, they're highly oxidized to start with. However, academic literature has shown that some of the carboxylates like PFOA have been susceptible to chemical oxidation via different forms of activated persulfate, for example. In terms of PFOS breakdown, there's been less academic work done, and we've got some initial data from some trials of a technology showing that we've got some fluoride being released, but it's early days. This sort of treatment would be useful in source areas where you could inject into higher concentration areas and therefore break down these compounds in the ground. But there should be care taken that you don't get release of perfluoroalkyl acids from precursors whilst doing this, so make sure that the compounds can be broken down by the oxidants used to mineralize them as opposed to forming breakdown intermediates. Injecting carbon into aquifers has been tried for many contaminants, but not specifically perfluoroalkyl acids or PFAS. So in these processes, activated carbon is emplaced or injected into aquifers to distribute or form fractures. And the concern with this is, I suppose, there's no biological breakdown of these contaminants, which is normally what is used as a mechanism for making these applicable for conventional contaminants like BTEX or fluorinated solvents. But then also with these applications, uniform distribution of any of these particles seems very, very unlikely, as they're too large to distribute evenly and the particles will strain in the formation. So we've done a lot of work with emulsified vegetable oils of various particle size to show how they strain in the formation and how they distribute. And the larger size activated carbon seems unlikely to form some kind of perfect surface which will absorb contaminants. And the even larger form really is more fracturing it in via a direct push rod. So the concern with this is more how do you replace the carbon? If the carbon is in place and it saturates with PFAS, it then becomes a secondary source. So is that then a zone that has to be managed when the carbon's saturated? It becomes unable to treat any PFAS that's coming past it. And what do you do next? Do you have to inject more and keep injecting more? And then do you have to treat that as a secondary source in the future where it will just desorb these contaminants over time? So fungal enzymes have also been tried against various PFAS compounds, and they have been shown to be pretty effective against fluorotelomeres at causing partial breakdown. In that, if that perfluoroalkyl group has got an ethyl unit next to it, you can get some defluorination of these molecules. But you still end up with a perfluoroalkyl acid, generally a carboxylate like PFBA, PFPEA, etc. So there's some publications showing that a fungal enzyme has broken down PFOA via humidification reactions. I think the concern there is the scale-up and the reality of scale-up, and the evidence showing breakdown seems somewhat tenuous to start with. So the humidification enzymes will have reasonably low kinetics, require a supply of a mediator or cofactor and oxygen potentially. And so if you try and use this in the ground, they will be a good source of food, carbon and nitrogen for microorganisms, or in a water treatment system. So you will need some way of protecting them. So scaling this up seems fraught with potential problems, but still there's some interesting research evolving.
Thanks, Ian. So just to close this out, and sorry we're a few minutes late, some takeaway messages for you. You can see that the treatment here is tricky and it's not always straightforward. There's a lot of science still evolving. Hopefully we've given the audience some clues, or at least our opinions on areas where we see a lot of promise. Another thing that I think all of the presenters have hammered home is that PFAS chemistry can be complex, and there can be a lot of other compounds present. So that's really a pre-design CSM consideration. I think just think about your systems with agility and just to be ready if those things come up in the future, so it doesn't require a completely different technology. Another take-home is to really think about things in terms of the treatment train. There's a lot of GAC-based systems that are going in right now with sometimes very reactive, without very little consideration for the O&M burden that may bring onto the project or the team. And there's definitely ways to lower that O&M by being smart about the treatment train, pre-treating, using combinations of resin and GAC, or some of the other more capitally intensive systems if we know we're going to have to pump and treat for a really long time. And with that, we're done. We appreciate everyone's interest, and feel free to reach out to us if you have any specific questions, and we will answer them. Thank you.
Okay, thank you, Jeff. We did have a few questions from an earlier presentation. Dr. Chris Lau, we're going to unmute your phone. And the question was, what is regarding the NHANES study, and what effects did the NHANES measure?
Can you repeat the question? I don't understand what is the gist, what you're asking.
Well, could you discuss the NHANES study that you referenced there? What did it measure and evaluate?
Okay, so the NHANES study is a very large, it's a survey. They take samples from across the country. It's supposedly they have a model to represent the country. So they actually measure a lot of things besides perfluorinated. I mean, they measure lead, cotton, and they measure the wellness of the people. So whether they have any the cholesterol level, a lot of the factors, as well as the socioeconomic status, race, and geographic area. So it's published by CDC. So I think in order to get the actual data, you have to pay, but you can get a glimpse of the distribution. So over time, every entity can ask CDC to add on something that is very important that you want to track around the country. So EPA did that about 18, 19 years ago, I guess, and asked them to add on this chemical to the list of survey. So essentially, there is a very broad. So people actually can acquire the data set, and they look at some of the epidemiological study. For instance, they can look at the range of the chemicals. In this case, actually, the difference is not great because this is like real life exposure for everybody. And then they want to tease out, compare, well, in the higher level, do you have higher cholesterol, lower cholesterol? Do you have any illness, tumors, things like that? So it's kind of very broad. So you can actually go in and tease out any fine association. So I want to emphasize on association. So they essentially just look at what's kind of shakes out, rather than any real biological basis per se.
Okay, unmute me. Okay. All right, thank you, sir. All right, at this time, I'd like to extend our deepest appreciation to our speakers and you for attending. On behalf of the Society of American Military Engineers and the Environmental Committee, we appreciate your participation and hope that the webinar has been useful. We do have a survey for you to complete, and please answer questions so that we may tailor future education to your interest. Also, feel free to visit SAME.org/environmental, and you can reach any of the Environmental Committee board members through that web page. At this point, this concludes our webinar, and we wish you a great day. Thank you.
Well, ladies and gentlemen, that does conclude today's event. Thank you for joining us, and you may now disconnect your lines. Presenters, please hold for a moment.